Hi, my name is Talia, and I am a high school senior who's super passionate about teaching others chemistry and math. This YouTube channel is a supplemental resource to anyone who might be having difficulty in their chemistry classes. This week, I'm going to be explaining ionization energy and electronegativity. This is part 2 of my periodic trends discussion at the honors chemistry level. If you are in AP Chem, the explanations I am talking about in this video and in the previous video will not suffice for your level of understanding, and I will be making AP Chem level versions of these videos in the future. So without further ado, let's get started. Okay, so the first periodic trend we're going to be discussing in this video is ionization energy, which is the energy required to remove one electron from the nucleus of an atom. And this trend increases as the electrons get closer to the nucleus. So if you apply this to groups and rows, ionization energy decreases down a group and it increases across a row. So ionization energy decreases down a group because as you move down the periodic table in groups, a new orbital is added, so the valence electrons are farther from the nucleus. And ionization energy discusses removing an electron from the atom, but you always start with removing valence electrons. So if the valence electrons are farther from the nucleus, less energy will be required to remove them because of the higher principal quantum numbers of the valence orbital. Ionization energy increases across a row because, like we talked about in atomic radius, the number of protons increases, and then this increases the positive charge on the nucleus. So when the positive charge on the nucleus is increased, there's a greater attraction and the electrons are pulled closer to the nucleus, therefore making it harder to remove one electron. We're going to now practice 2 examples with ionization energy. First, we have which has a higher ionization energy, sodium or potassium. And the answer to this would be sodium, because sodium has valence electrons in the 3rd energy level and potassium has valence electrons in the 4th energy level. So the electrons for sodium will be closer to the nucleus than the electrons for potassium. I'm going to write that explanation down. Okay, so here's my explanation for the first problem. Sodium, this is a very in-depth explanation because I want to make sure that I discuss all the parts. So sodium has a higher ionization energy than potassium. Sodium has valence electrons in the 3rd energy level, and potassium has valence electrons in the 4th energy level. Since the valence electrons for sodium are closer to the nucleus than the valence electrons for potassium, more energy will be required to remove an electron from sodium than from potassium. So this is a very in-depth explanation, and this could be simplified more depending on what your teacher wants. I just wanted to make sure I put in all the details that would be explained most likely at the HP Chem level so that you have all the information. Next, we are going to talk about arsenic versus selenium, which one has a higher ionization energy. The answer will be selenium because of the increase in protons, which will create an increase in positive charge, making the electrons closer to the nucleus and making it harder to remove one. So I'm going to write down that answer. Okay, so here's my explanation for the second problem. Selenium has a higher ionization energy than arsenic. This part is in extreme detail. You might not always need to go in as much detail. Selenium has more protons than arsenic, so there will be a greater positive charge on the nucleus for selenium than arsenic. The electrons will therefore be closer to the nucleus for selenium than arsenic, and it will be harder to remove one electron from selenium than from arsenic. You could use harder to remove one electron or will require more energy. I just wanted to do both options. But you just want to make sure you're hitting those key points, that ionization energy is all about the distance, how close the electrons are to the nucleus, because the closer they are, they're obviously going to be more attracted to the positive charge and more energy will be required to remove one. So now we're going to talk about exceptions to ionization energy. So there are ions that are most stable when the orbitals are filled or half filled. And this then causes exceptions. So for instance, with aluminum and magnesium, you would expect that aluminum would have a higher ionization than magnesium, right? Because it has more protons, greater positive charge, just like we just talked about. However, magnesium actually has a higher ionization energy. And we're going to look at this with the electron configurations. So if you notice, I'm going to do this in a different color. Magnesium goes from 1s2, 2s2, 2p6, 3s2 to 1s2, 2s2, 2p6, 3s1 plus an electron, because you take away a valence electron with ionization energy. And aluminum goes from 1s2, 2s2, 2p6, 3s2, 3p1 to 1s2, 2s2, 2p6, 3s2 and an electron. So if you notice, magnesium has a half-filled orbital versus aluminum lost an orbital. It has a filled orbital, and therefore aluminum is more stable. So as you can see here, the resulting ion is unstable because it's an unfilled orbital. This resulting ion is stable because there's a filled orbital. And the same thing can be seen for beryllium and boron. Beryllium has a higher ionization energy because when it loses one electron, it has a half-filled orbital, versus when boron loses one electron, it loses the 2p orbital and just becomes 1s2, 2s2. So it has a filled orbital. The other kind of exception is from a half-filled to an unfilled orbital. So we can look at this with sulfur and phosphorus. You would expect that sulfur would have a higher ionization energy because it has more protons. However, phosphorus actually has a higher ionization energy. This is because if we look at the electron configuration notation, phosphorus ends in 3s2, 3p3. And then if we take away an electron, which is what ionizing does, we get 3p2 plus an electron. So we go from a half-filled orbital to an unfilled orbital. However, sulfur, the opposite happens. It goes from an unfilled orbital in 3p4 to a half-filled with 3p3. So we go from unfilled to half-filled. And this then makes sulfur more stable because it has a half-filled orbital. So then this causes the ionization energy for phosphorus to be higher than the ionization energy for sulfur because phosphorus becomes unstable. The same thing can be seen for nitrogen and oxygen because of a similar reason. Okay, so electronegativity is our next periodic trend, and it is the measure of the ability of an atom to attract the electrons of another atom when bonding to it. So when the electron shells of an atom are farther from the nucleus, it will be harder for it to attract the electrons of another atom in a bond because the electrons of the other atom will be farther from the nucleus of the original atom. So electronegativity decreases down a group, and this is because the principal quantum number increases. So the valence electrons will be located farther from the nucleus, and the electrons of another atom in a bond will be farther from the nucleus of the original atom. Electronegativity increases across a row. This is because as the atoms become smaller, which we already know happens across a row, the electrons are pulled closer to the nucleus. So the atom can more easily attract the electrons of another atom. The electrons of another atom in a bond would be closer to the nucleus, which would increase the electronegativity. Basically, as going across a row, the increase in protons, which makes the atom smaller, decreases the size of the electron cloud. So there's less space around the nucleus, so the electrons of another atom can get closer to the nucleus of the original atom. So now we are going to practice that trend with these problems. First, we are going to answer the question, which has a higher electronegativity, silicon or chlorine? So we are going to write the electron configuration notations as proof for these problems. So let's first start with writing silicon. Okay, so silicon is 1s2, 2s2, 2p6, 3s2, 3p2. And chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so chlorine is going to have a higher electronegativity because it's a smaller atom. So the electrons of another atom in a bond are going to be closer to the nucleus of chlorine than they're going to be closer to the nucleus of chlorine than silicon. So I'm going to write that explanation. Okay, so chlorine has a higher electronegativity than silicon because chlorine is a smaller atom. But I explained why chlorine is a smaller atom. There are more protons, which has a greater positive charge on the nucleus. And as a result, the electrons are pulled closer to the nucleus for chlorine than silicon. And the electrons of another atom in a bond will be closer to the nucleus of chlorine than silicon. That is the crucial phrase that you want with electronegativity. The electrons of another atom in a bond will be closer to the nucleus for blank than blank, because that is what electronegativity measures. So we are now going to compare magnesium and calcium. Let's write the electron configuration notations. We have magnesium, which is 1s2, 2s2, 2p6, 3s2, and calcium, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So magnesium is going to have a higher electronegativity because calcium has valence electrons in a farther energy level. So there will be more distance between the electrons of another atom and the nucleus of calcium. Okay, here's my explanation for this problem. So magnesium has a higher electronegativity than calcium because it has valence electrons in the third energy level. Calcium has valence electrons in the fourth energy level. So Mg is therefore smaller than calcium. So the electrons of another atom in a bond will be closer to the nucleus for magnesium than calcium. And there's our critical phrase once again. So that is electronegativity. And now we are going to practice all the periodic trends together. Okay, so we are going to do a practice with all of the periodic trends. There are two examples, rubidium and strontium, and selenium and tellurium. So write the electron configuration, determine which of the two in each example has a larger atomic radius, a higher ionization energy, and a higher electronegativity. And then which is larger, silicon or silicon 4 plus, and chlorine or chlorine minus. So try all of those on your own, and then I am going to show you the answers and we can discuss them. I'm going to go one by one with each trend, but first we are going to talk about the electron configuration. So feel free to check them. Rubidium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. Strontium is the same, but it ends in 5s2. Selenium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. And tellurium is the same, but it ends in 5s2, 4d10, 5p4. So I'm going to go with the first example and just go all the way down. Rubidium has a larger atomic radius than strontium because strontium has more protons than rubidium. So there's a greater positive charge on the nucleus for strontium than rubidium. And then therefore the electrons for strontium are pulled closer to the nucleus than the electrons for rubidium. So rubidium will have a higher atomic radius. Next, with ionization energy, strontium has a higher ionization energy than rubidium because it has more protons, so the electrons will be pulled closer to the nucleus. And I didn't talk about this, but same as the atomic radius, there will be a greater positive charge. So the electrons will be pulled closer to the nucleus for strontium than rubidium, and it will be harder to remove an electron from strontium than rubidium, so it will have a higher ionization energy. Finally, with electronegativity, strontium has a higher electronegativity than rubidium because of the more protons, and it is a smaller atom. So the electrons of another atom in a bond will be closer to the nucleus for strontium than rubidium. With this electronegativity example, I did not go as in depth as my previous explanations. I didn't explain why strontium is smaller. You can, if you would like, just to be safe. I conveyed it in my earlier responses, so it's not always necessary, but just make sure you're always doing what is asked of you by your teacher or by like your exam, or just what you need to do in order to fully understand the concept. Sometimes you might need to write in a ton of detail in order to get it, and that's totally fine. But just make sure you're hitting all the points. Okay, now with selenium or tellurium, tellurium has a larger atomic radius than selenium because of the location of the valence electrons. Tellurium has valence electrons in the 5th energy level. Selenium has valence electrons in the 4th energy level. So the electrons in tellurium are farther from the nucleus than the electrons for selenium. That's why tellurium has a larger atomic radius than selenium. Selenium has a higher ionization energy than tellurium because of the valence electrons, which we already mentioned. So the electrons are closer to the nucleus for selenium than tellurium, and more energy will be required to remove an electron from selenium than tellurium. As you can see, I wrote that explanation slightly differently. I didn't say that it's harder to remove one electron. I said more energy is required. Same kind of thing. And then also I switched the order of describing where the valence electrons are, just because I tailored my response slightly more towards the prompt. You can write it either way, just again, as long as you're conveying all the necessary information. Finally, selenium has a higher electronegativity than tellurium. Same thing with the valence electrons. So since selenium is a smaller atom, the electrons of another atom in a bond will be closer to the nucleus for selenium than tellurium. Okay, now which has a larger radius? Silicon has a larger radius than silicon 4+ because it has more electrons. And with a cation, there's an orbital that is lost due to the losing of electrons. So cations have one less orbital than their neutral atom and therefore are smaller than the neutral atom. Chlorine minus has a larger radius than chlorine because it has more electrons. And something you'll learn in AP chemistry, there is therefore more repulsion, which creates a larger electron cloud. So that concludes our discussion on periodic trends. As you can see, my responses were different throughout the whole thing. They don't have to be word for word. You just want to make sure that you understand completely what you're doing and you're writing your responses to include as much detail as possible. And everyone obviously makes mistakes, but it's better to learn this information rather than memorize it. So truly try to think of why these trends work the way they do. And then that'll definitely help you a lot with your explanations. So that is this week's video on ionization energy and electronegativity. I hope that you got some more understanding of what you're learning in Honors Chem. I also hope you enjoyed the video. Remember that these explanations are at a more Honors Chem level, and I will be making AP Chemistry versions of these in the future. If you have any questions, feel free to leave them in the comments, and I'm also going to leave a link in the description of my website where you can schedule tutoring if you would like. If you need help with Lewis structures and polyatomic ions, that is what I will be going over next week, so feel free to join me back if you need to do so, and good luck with learning your chemistry.